Welcome back. Summary of properties for 3D vectors. If you're getting to this particular point in your studies of vectors, you're getting closer and closer towards the end. Now, I'm going to talk about in this video two set of properties. One set is going to be with regards to addition, and then the other one is going to be talking about properties of the dot product for 3D vectors. So let's break these down. I'm going to actually also prove them for you. You might think that the proof is rather elementary, but I do think that it's worth your time to walk yourself through each of the proofs to understand how do you actually show a particular property and then why is it true. It may seem not very useful to you, but if you do go on into studies of, for example, linear algebra or algebra in general, later on in post-secondary, then understanding the actual properties and getting a glimpse of how to prove them is definitely a good tool to have handy. So let's break these down. So the first one is the zero vector addition. Well, in 2D, we have certainly shown this, and in 3D, this is no different. This particular property just simply states that if you take a vector, so if you take a vector v, and you want it to be able to add the zero vector to it, well, it should not surprise us that the result is going to be just the vector itself. And of course, if you wanted to show this directly, how you would do this is in this particular way. So you can take each component. I'm going to take them as the Cartesian actual components of each. So Vx, Vy, and this will be Vz. That will be your V vector. And then your zero vector can be simply 0, 0, and 0. And if you're going to be adding these two together, so if you add these two together, then of course Vx plus 0 is just Vx. That's what you're going to get there. You're going to get Vy plus 0 is just Vy. And you're going to get Vz, that component of the z will be plus 0, and you're going to get a result of Vz, which of course is exactly what we have over there. So that is the zero vector addition. You can also do the zero vector addition, especially when you combine it with the commutative property. So you can state that the zero vector plus a vector is equal to just the vector itself. So this is the first property that we have. And I'm going to kind of remove this for the moment so I can concentrate on the second one. So here is the second property, which is the scalar identity. This particular identity refers to if you are going to be multiplying a vector just simply by a scalar 1, where 1 is literally just an actual whole number or an integer number or a natural number. So if you multiply by 1 any vector v, again, it should be no surprise to us that what we're going to get is we're going to get the vector v back. Now, in order to show this, again, it seems kind of elementary, but if you break down your vector in terms of your components, vx, this will be vy, this will be vz, this is what you will have. And of course, each component multiplied by 1, so if you take the actual components and multiply them by 1, you're going to get Vx back, Vy, and Vz back. And that is exactly what we have there on the right-hand side. So that scalar identity property is nothing special. And in fact, it does pertain to the kind of distributive property that we would have. And we're going to get to that one, in just a moment. So you can come back to that. Now, the commutative property, which is the next one on our agenda list right here that you have. So this is this particular property. What this says is now if you have two vectors and you're adding them together, so let's say v1 plus v2, and you wanted to add them together, it does not matter the order. So which means you can take V2 and you can add it to V1. This is called the commutative property or commutative property. So in terms of pronunciation, so I guess it's the commutative property, if I want it to be correct. Now, where does this come from? Of course, you can do exactly the same thing. You can break down each vector, so V1 in terms of its x component, V1 in terms of its y component, V1, okay, in terms of its z component. And if you're going to be adding it, maybe I'll shift this over a little bit, and if you're going to be adding it to the second vector right here, this is going to be V2, and this is going to be its x component, V2 of its y component, and V2 of its z component. Now, if you're adding them together, so the addition of the vectors, it's just each individual components. So these two components will add. That's going to give me V1x plus V2x. That's what we're going to have as our first entry. Then you're going to get V1y plus your V2y. So that's going to be the second entry. And then finally, you're going to get V1z plus V2z. And that's going to be your third entry. And now under each particular entry, you can now go back and reverse this. So you can say, well, of course, these are just two scalar items, and the scalar items in terms of their addition, well, they are commutative themselves. So you can rewrite this as V2x plus V1x. That is exactly the same thing. And of course, you can do that to each of the components right there, right here, and you're going to get back your result. This is now going to be V2y plus V1y, or V2z plus V1z. And of course, this right here is the reversal. So now you can say this is just simply V2. My apologies here. Let me just rewrite this. V2x, and then this is going to be V2y, V2z, plus, and then your V1 x, V1, this is going to be y, and then V1 z. That's what you have right there, which is just V2 vector plus V1 vector, which now shows you your right-hand side. Now, this is very tedious to be doing this, but indeed, this is how you actually would proceed if you wanted to be able to show that property. So that is the commutative property right there that we have. Let me delete this out. Now, what about the associative property? So this particular property, what does this one say? Well, this one is actually really interesting because it allows you the addition of vectors, and it is irrespective of the actual order. So what you have is, if you have two vectors, let's say it's V1 plus V2, so these are the two vectors, and you wanted to be able to add them together, and then you had another vector that you wanted to be able to add right here. Well, it turns out that the associative property means that you do not have to add your first two vectors and then add your third vector to that resultant, because notice V1 plus V2 will give you one vector as a result, and then you can add V3. It turns out that the associative property states that this is the same thing as, for example, taking V1 plus and actually combining V2 vector with V3. So this is really neat because it tells you that the order of the additions is irrelevant for vectors, which is great, so that you can actually take these vectors and work with them, whichever one is going to be easier for you. Now, to show this in terms of actual components of each, we would have to take the V1 and then break it down into its x, y, and z component, or z. We'd have to do the same thing for your v2 vector and then v3 vector. And then you would be doing the actual additions. And then you would notice that you would come up with this associative property. So it would follow exactly the same steps as your commutative property that I just did. And this is really important, okay, for us. Now, where this comes into play is, for example, if you're going to have 3 vectors, which are added together, or more, like this, then it doesn't matter what you're going to be actually doing in terms of associative property. It doesn't matter where you start. You can certainly start with adding these 2 vectors, or you can say, well, maybe these 2 are easier, so I can do that, and I am guaranteed that the result will be the same. This seems elementary to you, but actually for vectors, it's really important. For numbers, if we had just 3 numbers, of course, if we're going to be adding them together, the order doesn't really matter. Well, the same thing holds true for vectors, which is really neat. Now, the other part, which is really cool, is sometimes you will find that you can combine the commutative property with the associative property. And what I mean by that is you can actually swap these. So for instance, if you don't want to be adding v1 to v2, you can swap these 2 by using the commutative property, which will give you v3 plus v2. And therefore, you can actually add these 2 together, again by the associative property, or the other ones. Now, this is really neat to be able to just shift the vectors around as you like by the commutative property and then add them by the associative property in whichever order you like. So that is the associative property that we have in here. Let me get rid of this. Let me get rid of actually the whole thing so that it cleans it up. Now, what about the distributive property in here? So for the distributive property, what you have is, this one is actually pertaining to distribution with a scalar. So if you have a scalar, so within here, so let's assume that our scalar is k, and that particular scalar is some real number, and we want it to be able to add 2 vectors together. So let's say you had v1 plus v2, like so. Now, we know that we can go ahead and add these. Now, what the distributive property says is that what you can do is, if you wanted to scale the resultant, so this k, so you have your resultant, this would have given you a resultant vector right there if you added them together. Well, you can scale that resultant vector. Of course, that's nothing special. But what is special is that instead of scaling your resultant, you can actually distribute. So you can distribute this inside the actual brackets, meaning you can distribute it across each vector. And what you would have is, you would have that this is the same thing as saying k, okay, meaning you're going to be scaling your first vector, and then you're going to be adding it to the scaled second vector. And these 2 give you exactly the same thing. So this is going to give you this back. And that is another useful distributive property. So it's another property which we can use for vectors to make our lives a little bit easier. It means that we don't have to worry when we're scaling vectors which are the addition of 2 or possibly even more. So you can do this and extend this to multiple vectors in 3D. So it could have been v1 plus v2 plus v3 and so on, and you can distribute it across all of them. And this one, in terms of its result, okay, as you would be doing this, well, what this would mean is it would mean something like this. So if I would write this out in my Cartesian coordinates, I'm going to just put it like this. So v1, this is going to be the y component, this is going to be the z component or z component, plus, and then here is my second vector, so v2x, v2y, and then finally v2 and z or z. So what this is saying is that, yes, of course, I can add these up together, and if I added them up together, you would see that this would just simply be v1x plus v2x, and you would have v1y plus v2y, And then finally, you would have v1z plus v2z. And here's your k that you have. And now, of course, so within here, so you can scale this all together. So you can bring this now inside. So we know that if we have one singular vector, we are just simply scaling each of its components. So that component would have been k, and this would have been v1x plus v2x. I'm going to just do one component. The same thing would happen for the y and for the z component. So you would have that. And what I wanted to show you is that now, of course, the addition is nothing else but the distribution across here. So you would have had k. This would have been v1x plus k of v2x. And then the same thing would happen with the y component and with the z component or the z component right there. And as you can see from here, this indeed would mean the same thing as if you actually just simply scaled each component and then did the addition afterwards. That's exactly what would have happened right there. So that property, which is the distributive property, is really useful. And then we can use this distributive property, of course, you've seen this in the scalar identity, where you're just simply distributing it right across into the actual vector itself. Those are the kind of 5 key properties of vectors. Now, I've only shown this for 3D. Of course, this holds true for 2D. I have actually done a video on that and mentioned those properties. But it also extends to n dimensions, so 4th dimension, 5th dimension. And if you do continue to study algebra, so 3D is where you typically stop in high school, because it's something we can visualize. But if you want to be able to extend and work with vectors in much higher dimensions, and now you might think, well, what do you mean by higher dimensions? They certainly do exist. It just means that you have multiple things, not just our viewpoint of the world, which is in 3D. You can start adding more dimensions. The only thing is you won't be able to visualize these very well for yourself, depending. Maybe you have an abstract mind, which is not like mine. I certainly have a difficulty in trying to visualize anything. Okay, it's even hard to visualize 3D for me. So those are the actual properties that we have in here, and we can apply each of those properties throughout, okay, and then be adding vectors to see those. Now I'm going to put up a link up above there to the 2D explanation of these properties as well, so you can glance back. Now, the next item is going to be a discussion of the dot product properties. Okay, so here's the dot product. So we have 3 key properties to think about in terms of the dot product. So the first one is the commutative property. And if you recall, the commutative property for addition means that we can add the vectors and the order of the vectors is irrelevant. Well, with the dot product, if we do have 2 vectors, here's my first vector, and I'm going to take the dot product with the second vector. The commutative property states that we have the order, again, is actually irrelevant. So we could have started with v2 first, and then we could have had v1 second. This, again, is just simply convenience. You can go back and forth with these dot products, and you can see what the result would be. Now, if you are dealing with 3 dimensions and you're thinking about the Cartesian representation in terms of the vector representation of each, well, showing this is not very difficult. Again, you would just simply take each component. You would have v1 components right here, which I'm writing out. And then if you dot them with the components of v2, so that's going to be v2x, v2y. So those are your components right there, while the dot product is just the multiplication of each that we have. This would be v1x multiplied by, so this is times v2x plus, and then we do the same thing. So with the y components, and then with the z components or the z components right there. and that is my dot product. And now, obviously, so each of these right here, because it's just multiplication of two scalars, so it's the x components, this is the same thing as saying v2x multiplied by v1x, and then the second one is the same thing as v2y, v1y, and then the last one is v2z multiplied by v1z. Now, of course, that reversal, because that comes actually from the commutative property of multiplication just of scalars, which you have done all the way back to elementary school. Well, this is the same thing. So if you take this out, this is just simply v2 dotted with v1. If you are going to be taking this as the dot product, which is your commutative property for that. Now, this is, really nice to be able to use, okay, and kind of remember that the order does not really matter for us on the commutative side. So that's one of the properties. The second property, the associative property, actually deals with a scaled version of the dot product. So if you think back of the associative property for addition of vectors, so you had three vectors and we said that it does not matter if you're going to be associating, okay, so how you associate your addition, if it's going to be the first two or the last two that you're going to add first together, so how you associate two vectors together. Well, with the associative property for the dot product, it has nothing to do with addition because we are talking about the dot product. So if you have one vector dotted with another vector, the associative property simply states that if you're going to be multiplying the dot product of two vectors together by an actual scalar k, so k again is just simply nothing else but some real number, then you can associate this in such a way that this is simply equal to same thing as just scaling one of the vectors. So this is not the distributive property. You're not multiplying each of the vectors, okay, because this is not addition. It's a little bit different. This is actually the association. So what we can say is that this is going to be equal to times the dot product of v2. So you can associate the k that we have with the first one, or you can associate the k with the second one. This right here is going to be exactly the same thing. So that association that we have of my scalar value, so just some number, you can either do it with the first k or the second, and all of these are equal. And again, you can certainly show this for yourself. So you can take each component of vector 1 and then vector 2, write them out, find out the dot product, and then just scale it. So it's going to be k times each component. And then you can associate that k either with the first component of the v1, or you can associate the k with the first component of the v2. So this association that we have, this right here, it doesn't matter if that k actually scales your first or your second, and then you take the dot product between them, or if you just take the dot product directly and then you're going to be scaling it by k. All of these are the same. So the association with the scalar is either to the first or the second. The last item within here, so which is the distributive property, this one is actually really neat. Distributive property with respect to dot products, it means that if we have, so for instance, two vectors like so we have v1 dotted with, and sorry, I apologize there. So if we have v1 not dotted, let me just go back, and we want to be able to add this to another vector in this way, so we have v1 plus v2. Now, if we come along and then we say, well, what if we wanted to be able to dot this with, for example, another vector v3? Now, we know that this is going to be a resultant vector right here, and we can certainly do the dot product in this way and then find out what that is. It's going to be just a scalar value. But what the distributive property states it states that you can either do this, or you can distribute the dot product inside of your bracket. So instead of adding two vectors together, you can actually take your third vector and dot it first, and then the addition of the two, so like you see I'm doing right here, that particular addition that we have, I have distributed my vector v3 onto each one, and it is equal to exactly the same thing. Now, because of the commutative property, you can now switch the v3 and the v1 and the v2 and the v3. So you can switch this with this. So this will be first, this will be second, and then you can switch v2 and v3. And what you will find is you're going to get v3 dotted with v1 plus v3 dotted with v2. And of course, now you can factor that out just as you distribute it out. And therefore, so notice this is what we're going to get. So it doesn't matter if the dot product comes first, okay, or if the dot product comes last. So notice here I put it last, and then here I put it first. All of these are actually equivalent. This is equal to that, it's equal to this, and it's equal to that. And that is because of the distribution of the dot product. And once again, if you wanted to be able to show this, you can break down each vector. So I'm not going to necessarily do this directly, but let's say I just want to get you started, and you can try this on your own just so that you get acquainted with it. So let's say that's my v3, and I'm going to just kind of show the last one here. And then you can break down, so you would have your two components. So this is v1, and you would write this one in terms of its components, and then you would add it up, and this would be your v2 in terms of its components. So you can go ahead, set it up in this particular way. So you can add those together. Then once you do the addition, so of these, so as you're going to be adding this to that, you're going to just get a new vector, which is your resultant vector. And then you can apply the dot product, so you can multiply through, and you will notice that as you distribute, right, because now it's going to be distribution across just scalars, you're going to be able to find, okay, that you're going to be running into this right here. So you're going to go back, okay, one step here, then you can swap them, you can come back in here, and then of course you can remove it, okay, and then you'll come back to this. So that is a neat exercise. I would encourage you to go through this exercise and then try to see how that distributive property works. Now, when you are being taught this in grade 12, or maybe in the beginning of your first post-secondaries, maybe in physics or something of that nature, you're not going to appreciate these particular properties as much. But without these properties, if they do not hold, then basically all of our algebra starts to break down, and it just doesn't make any sense. So these properties do have to hold in order for us to have the algebra we have and that we take for granted to be able to work in the real world and solve various problems. So these properties, I know that they're very theoretical, but they are very applicable, and they must hold for our practical application of these algebras, vectors, and so on, so that we can manipulate them and do what we do with them. All right, so that is it for this particular video. A little bit lengthy in terms of these properties, so just a summary. I hope that you found them useful. Take care of yourself, and we'll see you in a future video. Bye, everybody.